Yo. What's up, Welcome back. Today we're working on my operating system for x86, written in Rust. Right now it has a few of like the basic features kind of laid out. It boots, it has memory allocation, it has async await, it has serial VGA logging, unit testing, clock interaction, PCI interaction, Ethernet. So if I run where we are right now, after setting up my environment correctly, this launches like a qemu virtual machine. We saw logs in like the VGA window, which would be on the monitor if we were on a real OS. We see some like heap allocations for like a vector and a map. So we've got allocation work, and we see like a date time that we pull off the RTC that is sane by some metric. Right, like we are in September 27th, 2023, which matches today's date. And probably this is 7 hours ahead of where I am because I'm in PST, so this is 21 o'clock and it's 2 o'clock here. Or sorry, the mixing units, 21 o'clock and it's 14 o'clock here. And we can like change the time. We can read the MAC address from the card, and we can like send and receive a packet back. So we like send a packet, we wait a little bit, we sleep, and then we get the packet back. And all of this is working in like the only thing we've been provided is like the bootloader loads us. So what I wanted to work on today is we have proven our Ethernet driver only kind of minorly. We have this state here where we set up our a couple features or like async code blocks in Rust. One to read, just print what it gets from the Ethernet driver as a raw string, and then we write a raw string to the Ethernet controller. And when we run it, we do in fact get back what we sent. That's words in English right now, but really we want to be able to parse something from like the outside world who wouldn't be sending this. They would be sending like a UDP packet or something. So what I wanted to look at is seeing if we could get that hooked up and maybe correctly extract some info from like a netcat frame that we send from our host. So that's what I want to do today. So that's intro done at around 2:48. Okay. So let's take a look at that. So we have our driver, RTL8139, and in here we're currently using loopback mode. If we get this with loopback flag in our constructor. So the first thing we want to do here is let's just ditch this send thing for now. We're not going to use this. We no longer need to like send a packet from ourselves to receive it. So let's get rid of that. And then we also want to construct the driver with loopback off. So we'll turn that feature off. And now we need some way to like send a packet from the outside world. So if we run right now, we should just hang forever because we're just waiting for a packet to show up. Oh, this is bracket loopback. Let's fix that. Where is that said? So we should just wait forever until we get a packet. And unfortunately, with QEMU's default networking mode, you can't actually send a packet from your host to your guest. But you can, well, directly, but you can like port forward. I'm not really exactly sure why that is, and eventually we'll have to do like a proper network interface that has all the features that we need. But for now, I think we can get away with. There is this port forward command that you can add to the network device. So here, you can say, I think it's host forward. Let's look it up. It's host forward. We pick what's the type of the port, where we're coming from, the port that we want to send to, and the guest that we want to send to. So here's an example here. And let's just paste this in here. And let's do UDP because TCP is more complex and we want to just get like the simplest thing working first. And this seems pretty reasonable. So if we send to port 6001 on our host, we should be able to receive on port 6000 on our guest. So let's take a look at that. So if this is working correctly, we should be able to say netcat -u for UDP, our local host And what do we say, 6001? Okay, so we do have some form of confirmation that when I run some code here, like I send a packet, we are now no longer correctly parsing a UTF-8 frame, UTF-8 string, which makes sense because we're no longer sending just raw UTF-8. We're sending like a packet, right? And these packets have like structure to them in some way. So what would be interesting though is if we could maybe find, it'd be nice to see what's in here. So let's maybe just say, you know what, screw you. Just print it as if it's UTF-8. And let's try that first. So here we had a send test. And what's interesting is we don't see anything that resembles test in there. So why would that be? Let's maybe look at, let's turn on our debug logs for the network card. So I can't remember where that is, logger in it. Here we can say that we want kernel RTL8139 to have log level debug. And this needs an into, and this needs to be an array. So what's happening here is this is supposed to be like a map of strings of modules to kernel levels. And so what we do here is we construct like a flat array of these things and then ask Rust's like type system to convert this into a hash map for us. And we need to like convert this like string into like a stack allocated string into a heap allocated one, etc., etc. But now when I run, I should start getting debug logs about our RTL8139, so we're chilling. And if I write the word test here again, I see that I received header 1, received buffer length 60. We see that we got around 68 bytes written, and our total buffer length, okay. So maybe we can start looking at something in here to try to prove to us what we want, to prove to us like what's happening. So I would think that somewhere in this UDP packet, we should just have like the raw string that was passed. So let's look at what we expect to get in here. So if I look up what's in an Ethernet frame, let's see. Somewhere I've seen like a picture of the whole frame. Where is it? I swear that there was a... Oh, this is what I was looking for. How come... Oh, I just scrolled too far initially. So we should be seeing this stuff. So maybe the first thing that we should do is we should start just like looking at what we get in here and see if that looks sane. Because we have no Ethernet frame parsing yet. Oops, didn't mean to double that. So maybe in main for now, we'll just start trying to parse this packet. So what does that look like? We'll probably have like an Ethernet frame type. And maybe he just holds a pointer to the data, or maybe he holds the slice. So we can just kind of put the packet in there. He's got a lifetime associated with him now because it's a reference to a packet. And here we can say Ethernet frame packet. Okay, so now what we can start doing is we can start like implementing some helper functions on this guy that will like print out specific parts of him. So let's look at that. So the first thing that we should see is the, oops, where am I? Like the first thing we should see is the destination max. So this should be a U8 slice, maybe. And this takes in self. And so this should be self packet, and 0 to 6. And we do the same thing for source MAC. So we have a source MAC address, also 6, but this is from 6 to 12. 802 1Q tag. So we'll say, just write tag here, because I think we can't start a function with numbers. And this will also be a U8 for now. U8 slice, sorry. And this is from bytes 12 to 16. Ether type is same thing, but self packet. This is 2 bytes, so this should be 16 8 to 18. Then we have the payload, which is everything except for the length minus 4. So payload is everything except for self.packet from 18 to self.packet.land minus 4. And the CRC is the last 4. Like this. Okay. I'm remembering from last time, we actually chopped the CRC off this guy because we didn't want to put that in the output, but we actually do want that now because we're parsing the frame externally and the CRC is an important part of that. And I guess we can start just like checking if this is sane. So let's make like a little debug implementation here. So there's a core format debug that we can do, a trait that we can implement for Ethernet frame. And what that'll do is when we print, if we try to like print this frame directly, it'll just like call our custom function here to format it. So we can do like, we could just like iterate over all these functions actually. So we can just copy all this. This is our quick way of writing code, is just massive copy paste. We take this same area, right, and we say filter out everything that doesn't start with function. So it's everything else but function, delete it. Now for each of these, we can say just take off, give me the words that are these functions. And then for our formatter, what we're gonna do is we're gonna write this. Actually, let's make this a MAC. We're gonna write the MAC address. So we're gonna say that the destination MAC is this, and then we're going to just print the same thing there. And we can do that for all these, right? And then here, this should actually say self.destination MAC. So we have to quickly turn these back into function calls like this. And we have to change all these to debug or else we won't be able to print them. And it's going to get mad because each of these needs to propagate errors that could happen from writing to the formatter. And we're chilling. So we have like a debug implementation now, and now if we go back over here and we say print my packet, we'll say print the Ethernet frame. Let's see what we get. So let's go back over here and write out our test. And we forgot to make these right line. So let's try that again. Because they were kind of like densely packed here, so it's hard to read. Okay. So here in our payload, I guess the question is, do we see the phrase test anywhere in there? And it's hard to tell. But maybe this stuff will give us some clues. So let's go back here and source MAC, we're going to print these as hexadecimal because that's how they're presented everywhere else in the world. And let's just start like looking and seeing if they look sane. So here, if I write test, we get a source destination MAC of anything, source MAC of this. Let's see if that matches anything that I have on my machine right now. So I should be looking for 5255A. Can I grep for like a colon? 5255A. No, that doesn't match anything. And do I get the same thing if I do this again? 5255A 022. Maybe that's like an internal qemu MAC address though, not like something that should match something on my screen, on my machine. So maybe that's okay. The destination MAC is like the broadcast address, so saying like qemu's forwarding it, saying like, I don't really know what address you're going to have, so I'll just send it to everywhere. That seems reasonable to me. The payload here, actually, hold on. I want to be able to do this in a loop. So let's just say loop here on the receive. And then I can like vary the string that I'm sending and see if that changes. So if I type like test or test2 or test3, all of these look the same. And weirdly, the CRC is the same on all of them. So something here is like going like pretty wrong, right? We're definitely like getting packets from the network. We're seeing the length, or we're seeing, sorry, the pointer to like where we've written to from the Ethernet device. We're seeing that increment, but like for some reason we're not seeing like the content that we sent. Now, for sanity's sake, let's set up a listener. So I just want to make sure that like when I'm sending over UDP to this port, if I like listen not with my OS but with Netcat, do I in fact get the data back? And I do. And it would be nice if we could maybe see like the raw data that's coming in here. Do I have Wireshark installed? No. Because that would give me like a really good clue for if I'd be able to like see what the difference between what I'm seeing here in the payload is and what like we're sending, you know? Wireshark. So can I capture from loopback? Ah, shit. I don't have sufficient permissions. Which makes this kind of hard. I would have liked to be able to do that, but I don't really want to like fuck with my permissions because that requires like a re-login, I think. And that would make me like end the stream. And I don't want to do that right now. So we'll skip that part for now. But we do have like some confirmation that like at least Netcat is sending something sane. And we understand that like this is a UDP packet that should have the data contained in there somewhere. Which means that we can start like trying to like unpack what we're supposed to see here. So let's try this again. So cargo run, test 2, test 3. So the fact that this isn't changing is concerning. So I guess we need to start looking at the Ethernet card and trying to figure out why it's not changing the data. So Ethernet frame validation is what we're going to call what we're working on right now. Okay. So I guess the first thing that we would want to do is, even though we don't have Wireshark, we could spin up a little application that just prints out what it gets from a UDP frame using like normal Rust. We wouldn't be able to check the Ethernet frame, but we should be able to check that the payload is something sane. Right? And how would we do that? Actually, I don't know if Linux gives us the tools to see the UDP frames directly. I think you can do like a raw socket. Raw socket. How do I use a raw socket in Python? I think I've seen sock raw somewhere. Yeah, here we go. Here we go. So let's see what happens if I write like a little quick Python script and try to do this. So we can say socket get by host name. I've never seen this before, but oh, I don't even know what this, we don't need this. We can say socket.socket, this guy. No lets in Python land. And we need to bind this to localhost. And we're doing port 6001. Could you have used sudo to get Wireshark to work without setting up the perms properly? Yes, except that this account doesn't have super user permissions intentionally because I don't accidentally want to leak stuff on stream like that's important. So I intentionally like have like a separate account for streaming that doesn't let me do that. And I just would have had to, yeah, it's something that I need to set up. But for now, I'm happy to just try this. Include IP headers, receive all packages. Let's just do this for now. I don't really understand what this include IP headers says, but this makes sense to me. This maybe, I wouldn't be shocked if I don't have permissions to do this either, actually, so. But let's see what we get. So Python 3 test py. I forgot that I need brackets here in Python 3 land. Protocol not supported. So that's not shocking to me. So that might be also a permissions problem. Okay. Well, that sucks. But I don't really, I guess it's hard to know why. But if that's crashing on the sock raw thing, then I'll bet you just raw sockets need special permissions. Permissions. That's my guess. Yeah, we need capnet raw. That makes sense to me. Okay, so we don't get that capability, unfortunately. So I guess we'll just go back into the OS and see if we can try to gather some information in here, based off what we're seeing. So I guess the same thing to do is let's like validate what we got. So let's see what the RTL 8139 provides us in terms of validation. The thing that's like running through my head right now is like, what bugs could I have written on the receiver side? And I'm definitely skeptical that I'm waiting long enough for the full packet. Because what I'm doing is there's like this circular buffer that the network card is writing to. And it says here that the sequence of events is that it like increments the pointer last after writing all the data. But I'm kind of relying on that to be true. And so what I could maybe look at is, does the CRC that I'm getting match what I expect? Right? So here in our Ethernet frame, we are in fact getting like a CRC for this data. And so I guess what I want to know is, I would like to calculate the CRC for the data and see if that matches what it's received. Probably something else that I could do as well is I could try to send a UDP packet back to the host and see if Netcat prints that. But for now, let's look at this. And let's look at the header as well. When we receive, the Ethernet card might tell us something about what happened. So here we're saying received header 1. And the packet header, the value 1 says receive okay. Nothing else in here is set. So multicast pack set to 1 indicates that a multicast packet is received. So this should be a multicast or broadcast packet because we're sending to MAC address FFFFFFFF. So unless my broadcast address isn't set. Yeah, I kind of want to take a look at that. I guess the question would be, why would I be getting anything at all if it wasn't going to the right place? But we do see this like destination MAC is not my MAC, right? I have a MAC address of, where the hell is it? Oh, I have a MAC address of 1, 2, 3, 4, 5, 6, 7, 8, 9 or something. I thought that I'm supposed to see it. Am I crazy? Waiting for MAC address here. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. So my immediate question here is, why would my received header not flag that this is not my MAC address? So let's look into that a little bit. RTL 8139. So somewhere in here, I set some pretty aggressive receive rules here, where I set something that said receive every packet ever. So let's double check the docs here. So this is receive configuration comes from 044H receive configuration register, and somewhere in here I say, what do I want to accept? So let's look at that. So here I wrote 0x3f, which is bits 0, 1, 2, 3, 4, 5, 6, and 7. I think. No, 0 to 6. And really, I shouldn't even be writing 6 because that's reserved. But let's see. Let's write this down to just if we understand correctly, I should be able, if I disable bit 3, then I shouldn't accept broadcast packets. And this I shouldn't see this. So let's see what happens if I do that. So I'll say, set bit, which is bit 3 to false. And it didn't like that because I made a mistake there. Set bit 3 to false. And I am still receiving it, so that's interesting by some metric of interesting. Let's just try setting this to 0, 0, right? Theoretically, we shouldn't receive anything if we've told it not to receive anything. So that's a good sign. We're no longer getting anything in. And if we set this to 01 to accept all packets, I think is what this said. Yeah, that gives us something. So set to 1 accept all packets with a physical destination address. So now let's try, we know that this is all packets, and even if these guys aren't set, this guy will accept it anyways. Let's try being a little bit more strict and try setting broadcast and physical match, maybe. So we'll set bit 1 to true and 3 to true, because that should be broadcast and physical match. And I'm just trying to get any intuition about what's happening here. So this does work, and this shouldn't be a physical match. So if I set broadcast to false, this should stop accepting. Okay, so what we've kind of just proven there is that the card itself is correctly flagging this as a broadcast packet. So that means that my understanding that the FFFFFFFF in the frame is being parsed as broadcast, that's all working fine. So then the question becomes, why do I not see that reflected in the received packet header, right? Because here, not here, here, the packet header should say have bit 13 set if this was a broadcast packet, if I understand this correctly. So if that is not true, does that mean that I'm parsing wrong, or maybe I'm parsing too early? Let's take a look at that. So in my receive get packet, I'm currently waiting. Oh, wait, this is a bug, I think. Hold on. Yeah, hold on, there's a bug in here. I'm waiting twice. This shouldn't change anything, but by the point I'm calling get packet, we should know that we have a frame. See, we have here, we basically, on read, we wait until our like 2 buffer pointers in our circular buffer here, capper and CBR is the other one. We keep track of when the 2 pointers hit each other, then we know that there's like nothing in the buffer, and we wait for those to move, and when they move, then we claim that it's like okay to read. Now, clearly there's something wrong with what we're reading, so this is like the first thing that I'm skeptical of, is that we're waiting too early. So what I'd be kind of interested in doing here is taking in like a sleep function, and this is going to be a function that takes in nothing and returns a like future that sleeps, I think. This gets like really complicated. This is the problem with using generic. So this future is of type, has a future. No, this is core future with output nothing. And then I should be able to call here sleep. This actually doesn't take in nothing. This takes in a time to sleep for. So we'll say sleep. This takes in like an F32 for time in seconds. And let's just like full on wait for a full second before we do anything. Right? If that, then we'll see if the data is different if we just give the card more time to process. So let's take a look at that. So in main, now we have to pass in our sleep function, which is like, the reason I'm doing it this way is because the sleep function is like complex and requires like some like tracking variables that we don't have globally accessible. So we'll say let sleep is a lambda that takes in t for time and returns this future. And it doesn't like that for some reason. Maybe I need to put these in curly braces. And then pass in sleep here. Here we go. Okay. So let's cargo run this. And what I should see now is after I type test here, I wait 1 second before getting anything. It doesn't like that at all, so I've done something terribly wrong. Let's just confirm. So I go back into this recall and comment this out. Interesting. I broke something. He said lambda, Rust communicate this man. Oh my god, I'm sorry. Closure. I said closure. Sorry, I've been in C++ land for too long. So something here is not behaving the way I wanted. Is this possibly because I removed this like receive waiter from the inner? No, that doesn't make any sense. What have I changed here? I've added logging, I've added like frame logging. The only thing I've really changed in here... Oh, oops, I forgot to set the broadcast packet back on. Oops. Init receive buffer. No. Here, this guy should be enabled. So cargo run again. And now when I write test, I get something. And now, if I uncomment this sleep, hopefully I wait a second before I get anything. Solid. Okay, so we do wait a second, and then let's just like kind of like huck some other stuff at it. And we're back. We're still in the same state of sending different data doesn't seem to affect what I get in the payload. So that's good indication that we're not just like reading too early. it could be indication that we're not like touching memory correctly. But we have some confirmation that the frame itself is at least somewhat valid, right? The destination MAC is in fact what we expect. The source MAC is a little odd. I would like to see, maybe we can look at like the qemu source code and see if we can find that MAC address stored in there somewhere. So what is the MAC address we're saying? 5255. 0x52, 0x55. Okay. 5255A022. So this isn't it. 52, 0x55. Is this anywhere? No. These are just like random test functions. Let's look up host forward in here and see if we can find its implementation in qemu and see what it's actually doing in here. Are any of these telling me anything useful? I just want to see like where this is implemented. SLIRP, I think is what I've heard is called user networking. I just want to see if I can like find the MAC address. But this is starting to get a little hairy. 52, 55. Yeah, I don't think I'm going to like have much luck searching that MAC address in there. I'm not even sure that it's hard-coded. That was just a guess. Okay, well, let's look at this other stuff though. Maybe if we look at the Ethernet tag and the Ethernet type, that'll give us more clues on if the data is valid. So we'll look at back to the Ethernet frame. And let's look at what ether types exist. 2 octet field, which protocol is encapsulated in the frame. So we should see UDP in there. And the value we see is 8601 or 1068. 8 big endian, I think, is network order. So we should see 8061. Which I'm not seeing on this list. 8601, sorry. 8601. So that's maybe a clue here that something's wrong. Oh, sorry, ether type, not... Oh, I'm backwards, sorry. Ether type, not tag. Ether type is 80, so it's IPv4. So we do, in fact, have indication this is an IPv4 packet. And... let's look at the IPv4 header. Maybe that will give us some form of clue. So this is some stuff we should see in there. This is already seems quite long, right? We're not really seeing... we have over 128 bytes in here. Is that correct? Source IP address. Oh, maybe this is in bits. Octet. Yeah, here we go. So the first 16 bytes are nothing, and then we have options after. Let's look at like what a UDP frame looks like. So when a UDP runs over IPv4, the checksum is complete, blah, blah, blah. So the pseudo header is not the real IPv4 header, is only used for checksum calculation. So I guess we should have... These don't really overlap nicely in my head. I was thinking that we would see like an IPv4 packet, a UDP packet in an IPv4 packet in Ethernet frame or something. So let's look at maybe the OS Dev Wiki had something on networking. And yep, so IP protocol sits on top of Ethernet, is required to send data on the internet given IPv4 address. And inside we have UDP, which does seem to line up. So maybe we should try to see if we can parse this as like an IPv4 frame. maybe that will give us some clues. Okay. So I guess if I understand correctly, this IPv4 frame should be like in the header. So maybe we just start pulling out some of these guys. Maybe we try to see if we can like read a source and destination IP address, and if they look like something sane. Where does like the UDP data go in here? Probably just after data. The packet payload is not included in this checksum. Blah, blah, blah. It must just come here, probably. After the first 16 bytes, we start seeing the UDP packet, is my guess. But that's a real guess based off like near zero reading. When UDP runs over IPv4, the checksum is computed using a pseudo header that contains some of the information from the real IPv4 header. The pseudo header is not the real IPv4 header. It is used to send IP packet. It is only used for checksum. Sure. UDP field length is like the UDP header and data. Sure. Okay, so let's. This guy doesn't say anything about like length or anything, but probably there is a like, yeah, the protocol, there's a protocol number in the IP header that should match UDP. So hopefully what we end up seeing here is we try to parse out the IP header enough that we can find this, and that'll give us some form of indication that we're working correctly. So that's here. This is byte 0489. So byte 9 in the payload, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nothing in here. I don't see UDP in here anywhere. That's interesting. That's interesting. I wonder why. I wonder if we're actually getting like an ARP packet or something. So maybe Netcat is like, we're like trying to find where to send this. qemu is like trying to ask us what our IP is or something, and we're not answering that, so we never get the packet. That would make sense. Sorry, when I say ARP, let's see if Wikipedia, ARP network, address resolution protocol. So I think what happens is when you're like looking for IPs, you might like say like, hey, I'm trying to send a message to this guy, or like who of you are that IP? Or it might also say like, hey, what IP are you, MAC address? I think maybe I'm misremembering, but there has to be like some way to find like which MAC address ties to which IP, and I'm pretty sure this is where it is. So let's actually see what IP protocol we are seeing in this maybe. So we have 6. This should be, protocol was the 9th byte. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're seeing IP protocol 2. Internet Group Management Protocol. That's cool. I don't know what the fuck that means. It's used to establish multicast group memberships and allows the network to direct multicast transmissions only to hosts that have requested them. IGMP can use for, so this would line up with how we've set up qemu here. We've said, qemu, could you please forward packets to our guest? And it's then maybe using this protocol to try to figure out which network card or something to send it to. Spitballing. I have no idea what's going on. I wonder if we specify here a UDP, like an address for the guest, if we start seeing different behavior. Does this look different? The CRC is different. That's good news. Still broadcast. Hello. But we are now seeing that 127001 in there, which is a good sign. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're still seeing IGMP, I think. But we are now seeing that like we're seeing different behavior. So this was 10.0215 before, and now it's 127001. Okay, so that let's see if this matches up with like what an IGMP message should have. Maybe not. Oh, here we go. So are any of these supposed to be the source address? So this is supposed to be bit offset 96, which is blech. What a pain. What a pain. Okay, so I'm pretty sure that I think this is right. Let's see if qemu user host forward IGMP. Let's see if that gives us any. Let's see if that gives us any clues. So this guy's saying that we use slurp multicast, and does he say the words IGMP anywhere in here? No. So that's not a good sign. But I think that there is good indication that we're getting data at all. This localhost making it in there is quite useful. So maybe let's parse the rest of this payload and make sure that I am right that we're looking at IGMP, and we'll kind of move in from there. So the source, this goes source address, destination address, zeros, protocol, UDP length. So does this match what we expect? Our payload should have a source IP address up front. This doesn't look like a source IP address to me. This does maybe. 10022. Oh, sorry, this is the wrong window. This is what I should be looking at. So we should be seeing protocol followed by checksum of 2 bytes, then source address of 4 bytes, des address of 4 bytes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is our protocol, followed by header checksum, followed by source IP, 1, 2, 3, 4. We are off. If we assume that the IPv4 header is keeping the destination address correct here, 127.0.0.1, we should have a source address before, 0000. Then we should have a header checksum of 2 bytes. Protocol, we still see protocol 2, if that's right. Blech. The version header in the IPv4 packet should always be 4. So let's see if that's right. If the first byte of the payload is 4, or the first nibble is 4, then we do know that the payload is supposed to be IPv4. So qemu in main is where we're working right now, and let's just look at the payload is frame payload. And if we look at the first byte of the payload and 0xf, this should be version, right? And our version, oh, oops, I have to send something. Version is 6. Okay, so the fact that the first pack version, it should always be 4, means that we're doing something wrong. But we could be looking at an IPv6 packet. We could be looking at IPv6 packet. which would suck. I would hate that. And I doubt that is what's happening. More likely, we have made a mistake on where the payload starts. Let's go back here and see if there's a chance of that. So this should start at 6, 12, 16, 18 is where we should see the payload start. Which is where we've done here. Interesting. Or length. I wonder if the ether type... No, okay. Not sure. Going back down, looking at this again. So we're seeing that the version in our payload is not what we expect. Was there somewhere that we're supposed to see that this is IPv4? We do see this 80 for the ether type, I believe, which means that we're IPv4. So the fact that our payload doesn't start with what is guaranteed by the IPv4 header is a little concerning. When it's optional, is it all zeros? How is that communicated? Yeah. I think that it might just be garbage. I'm assuming that for now, but I don't actually know. You're right that that's something to be thinking about. Like, that this might, in fact, not be there. But I don't know. Let's take a look. 802.1q consumes, this optional consumes additional space in the frame. Field size for this option are shown in brackets in the table above. Consumes additional space. So what does that mean? What does that mean? Yeah, it does look like, yeah, that's a good point. That it shouldn't necessarily be there. Good eye. Good eye. So maybe here we try making our packet payload 16 just to see. And here we do start to see it doesn't look better. The version field's still wrong. But you are right that it's like, how do we know? Oh, also, it says 4 bytes here. It said 2 bytes here. Also kind of odd. Also kind of odd. Oh, sits between the... Oh, source ether type field. Sorry. Ether type is always there, which is what we're seeing. But maybe this 802.1q header is also there. So we would actually have to add 4 to this. So this would be... if this was wrong, we would see that this is at 20 to 22. And we would see that this is 22 to the end of the packet, if that it's included. So here we would see ether type of 1. Does that tell us anything? Does that look like more sane to us at all? No. So what we had before was closer. So let's go back to that. We'll assume that there's no 802q header in there, and that this payload should be starting here if our ether type lines up. I guess what we could also try to do is we could try to like check the CRC and see if we compute the same CRC, do we get the same thing? And that would give us like some sort of guarantee that our packet is working, or that we like received what we think we should receive. So how do we do that? CRC computers. Well, is there just like an implementation I can like yoink? Here we go. Okay, I don't want to deal with this. Is there just like a CRC library I can pull in? Let's look at this guy. Looks like this would work, no STD, solid, so we can just cargo add CRC. I think. And we can just walk the packet and compute the CRC and see what we get. So how is this supposed to be computed? Implementation, blah, blah, blah. None of this. By far the most popular is CRC. I assume that we probably just go byte by byte. But I don't actually know. Ethernet, CRC. How do we even know if the Q tag is there or not? Yeah, I think that probably there's some way to check it. Based off just like quick sanity checks I just did there, I think it's not, but I could be very much wrong. Come on, someone tell me. Oh, this looks... CRC. The frame check sequence is filled by sending host. If the receiving host detects the wrong CRC, they'll throw away the packet. Sure. Okay. So let's just like look at the CRC API for that thing we just pulled out. And see what we do. So we can just pass in the whole byte string. Okay, yeah, easy. Easy. So that's a we start with an algorithm, I guess. I didn't think that I thought that CRC was well defined. I assume that there's like some default that we can just pull in here that everyone uses. Oh, wow, okay. I thought that this was simpler than this. Gross. So I guess I do just have to pass one of these in. Is there just like a default one I can use? Default. Nope. But they have an example here. Oh, I see. They have constants here that I can use. And I have to figure out which of these many are supposedly used by Ethernet. Rust, CRC, Ethernet. Ugh. How do I know? How do I know? So the CRC... Computation is left shifting at 30... CRC 32... CRC is post complemented. Here we go. This is promising. There's probably something in here that lines up if I read carefully. Gross. There's so many. So many. I wonder... Xfer? I don't know. Oh boy. Too much to keep track of. So, per the standard, computation is done using left shifting, CRC 32, initial CRC, FFFF, post complement, verify value, CRX. Standard states of the data transmitted least significant bit first, while FCS is transmitted most significant bit first. That's confusing. An alternative is to calculate CRC while right shifting 32. CRC's post complement verify value. Blah, blah, blah. Can I just like spin up the algorithm with those lines in? Whereas init... okay. I don't like this because if I get this wrong, this is complicated enough that if I calculated the CRC and I didn't get the right answer, I wouldn't be confident that if the bug was that what I'm receiving is wrong, or if I've implemented the CRC check wrong. So I'm not going to go down that road right now either. Okay. So what can I do to try to like gain extra context on what I should be receiving? I do feel like maybe I do just go back to looking at the fact that the payload is wrong is where I'm really feel like my head has to be at. Cargo run. Let's just double check here. So this ether type matching with IPv4, great. Works for me. Payload not containing the mandatory header is odd to me. So let's look at IPv4. Assuming it's not a Q-tagged frame, shouldn't we start reading at like 11 or 12? 6, 12. No, because the type is still here. So I think that this is 6, 12, ether type of... Oh, maybe you're right. Hold on, let's look at this again. Yeah, maybe you're right. Assuming this is not Q-tagged. So 12 to 16. And this should be 16 onwards. Maybe you're right. Let's look at that. Oops. Ether type is too long here now. Ether type should be 2 bytes long, so this should be 14. And this is 14 onwards. Let's just see if that lines up with something. Ether type 8.6 is now what we get here. And does ether type 8.6 also make sense to us? ARP. Okay. Good eye. Thank you for that. You just saved me a lot of effort. I thought that I double checked this, but you're right that this is not here. So we read too early. We weren't reading the right spot in the frame, and we were not getting this. So if this is an ARP packet, that might also make a lot of sense. That was actually like one of my initial guesses, and then I wrote that off because I wasn't seeing that anywhere. But let's take a look at the ARP. The ARP packet type. So here we should be seeing, we were seeing that we get this like address change to where we're sending to on the guest. And this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. 24 bytes in. Target protocol address. That seems reasonable. And then before this, we should be getting like a MAC address, 22, 2018. And he doesn't have that filled in. Okay, but if this is ARP, does that at least like line up here? Lots of zeros. We see 10222, 10222 back to back. Which... hardware type, 0. Let's see if that... So if this hardware type is 01, we would see Ethernet is 1. Okay. Protocol type 80. 80 for IPv4. That's looking pretty good. Hardware address length and protocol address length. Hardware address, so we should see 6 and 4. Yeah, this is lining up good. This is lining up really well. If we see the operation, 1 is for request, 2 is for reply. So we should be seeing 1 here for request. Now, we should be seeing sender hardware address, which is 82.85.10.022, I think, is probably what we're seeing. Does that line up with anything in my on my network card, I guess. Cards. No. But that might be okay. So this is 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0, 0, 0, 0. Let's make a real structure for this so that I don't have to just like count bytes off. So let's pretend that this is an ARP packet. And we will replace Ethernet frame with ARP frame. And in our ARP frame, we are going to have a H type, takes itself, and returns a U8 slice, which is self.packet 0 to 1, or bytes 0 and 1, so 0 to 2. We have a P type, which is 2 to 4. And we have hardware address. And this is going to be U8. So byte 5. And protocol address length. And this is packet 6. We don't need references here. Copying out. Operation is byte 6. Oops, this should be 4 and 5, not 5 and 6. This is the operation, which is bytes 6 to 8. Sender address is 8 to 14. Oops, this should be a slice. This should also be a slice. This can't be moved out, so this should be a reference. And sender address is 8 to 14. And this should be sender hardware address. And sender protocol address is 14 to 18. Why is this so short? Oh yeah, 4 bytes for an IPv4 address, sure. Now we have target hardware address should be 18 to 24, and the target protocol address should be 24 to the end. Or I guess to 28. Okay. So now we'll make a debug implementation for the ARP frame and see if that guy gives us anything of value. So we'll do the same thing we did before. We'll just copy paste this whole chunk into here and then filter out anything that isn't a function declaration. And then we can start doing some like vim macroing to say like write this. We go to the bracket and then say this. Yeah, something like this. There we go. You might be missing a string literal to format with. Because it's Ethernet frame, so this should be ARP frame. And we forgot to write in F as the target for all these writes. And we also forgot to put a question mark on all these. And we also forgot that all of these guys need to be debug, not display. So we'll do that. And now we should be able to parse this packet as an ARP packet. So we'll say let ARP frame equals ARP frame packet is the payload of the Ethernet frame. And we'll write down the ARP frame now and see what we get out. So now we'll send something from here. And we forgot again, once again, we forgot that these are all going to come out on one line, which makes them impossible to read. So we'll write line here. We will send our packet over. And that looks like a sane ARP packet to me. So we're sending from 10022. We're saying like, hey, are you 127.0.0.1? We don't know your hardware address, and we're asking you to give it to us. So probably I can just, if I respond to that ARP frame, maybe then QEmu's network will then say, hey, I am happy with that. Now I will send you the actual UDP packet. And if this is why we weren't receiving different data no matter what we sent over UDP, that actually makes a lot of sense because QEmu just doesn't know where to send it. Pretty cool, pretty cool. So let's try sending an ARP response. So we should be able to like, maybe we copy paste the existing ARP frame and just like start moving stuff around. Moving stuff around to make the response. So I wonder if we need to create the response, I guess. Like, or if it's just a copy paste of the same thing. So I wonder what these are supposed to look like. ARP protocol is like, am I only going to get Wikipedia? Like, I want to know. I just want somebody who has tables for me that I can just quickly glance at. ARP response. Did you keep the sleep in there? Do I feel like, yeah, there is a sleep in there, and I've just been ignoring it for a bit. And you're right, I should remove it. Here we go. ARP request, ARP response has a very similar packet structure. So here, the ARP request had a target MAC address 0000, and here the destination, I need to put the destination of who asked. The source is now my MAC address, and probably I just keep my own, I probably keep hardware type, protocol type, those are the same. Hardware address length and protocol address length are going to be the same. Operation is going to be switched from a request to a reply. And then I have to swap sender and receiver and fill in my MAC address. I'm pretty sure, I'm like 60% sure that if I just did that, it'll work. So let's try that. So here, I guess what we also what we'll want to do is we'll actually want these to be like mutable slices that we get back from our ARP frame, and then we can just like modify them in place. And really the only ones we care about for now are the these guys at the end and the operation. So keep it in and provide it later and say performance improvements. Yeah, that's pretty funny. Genius. Can I just like actually go in here and just like select everything in here and replace and with and mute? I'll bet you that'll work. Cannot borrow self.packet as mutable. Why? Behind an and reference. But I made it and mute. Cargo check. Am I crazy? Self. Oh. I see. Gross. Okay, so I guess what I'll do is I'll copy all of these and just make mutable versions of them. Gross. Okay, so we make a macro, research for function, we append mute here, we append mute here, we append mute here, and we append mute here. Okay, fine. Wait, it still isn't like this. Self behind an and reference cannot parse. Aha! I missed this mute up here. This should be lifetime a mutable. There we go. Now everyone's happy. And now I can say, here I copy the payload out into its own new slice. Response equals, just for now. We'll figure this all out later. So if I just copy out the payload, by doing like into to vec, this will give me like an allocated thing on the heap that I can work with. Now I can pass this in by mutable reference, specify them as mutable, and now I can start just like fucking around, right? I can say that ARP frame, I can try to swap the target addresses and stuff. So I can say, we'll say let ARP response is the same thing here, except we're gonna say our payload is now response. Like this. ARP response dot operation mute. We're gonna make this 1 now, I think is what we said. Operation is going to be 2, sorry, 2 for reply. Let's just double check the order here. Operations should be O2. We'll do this for now. We'll just hard code this guy like this. And he needs to be declared as mutable, of course. Now, the sender hardware address, mute is going to equal the original thing, which is the receiver target hardware address. Can I do an assignment like this? I cannot do that. Can I like core slice copy? What's the copy slice thing? Copy slice rust. Clone from slice. There we go. Okay, there we go. And so we have the sender hardware address should be the target hardware address, not protocol. The sender protocol address is the target protocol address. The target hardware address is the sender protocol address. And the target protocol address, hardware protocol. And there we go. This should be, so target protocol comes from sender protocol. Target hardware comes from sender hardware. Sender protocol comes from target protocol. Sender hardware comes from target hardware. Okay, now what I have to do is I have to replace the sender hardware address. Should actually be my MAC address. So this can be the RTL 8139 log MAC will also add a function that's like get MAC, which returns a U86. This. And then we just need to do the same thing here where we make a get MAC function, which returns a U86. And I guess we just do this. Okay. So now what we should be able to do is in here, our sender hardware address comes from self.rtl8139 get MAC. And this guy probably has to be like this. And now I should probably just be able to write out the response. Except that I don't have Ethernet frames. Fuck! Okay, I thought that I would just be able to like bang this back out, but it does look like we're not going to be able to do that before implementing Ethernet frames. So let's just look at this guy here. Where does he go? Where does he go? So I think I might have lost the Ethernet frame tab. Let's just pop that guy back open. So Ethernet frame Wikipedia. So preamble, we don't have to worry about. We just have to worry about this stuff. Oh, we're back to having to worry about CRC computation. Fuck! Okay. So we're getting pretty close. We know what we need now. We need implement ARP response so qemu can find us. We need to check CRC of incoming packet so we know how to compute. Implement sending of Ethernet frames. And okay, here we go. We are getting close to a proof of concept. So MAC destination and MAC source, these are easy to fill in. Ethernet type, this is also easy to fill in. Payload is easy. And it's just the CRC part that we have to handle now. So let's start here. Check CRC of the incoming packet. And maybe these are all kind of like subsets of this. Okay. So frame check sequence is a 4-octet cyclic redundancy check that allows detection of corrupted data within the entire frame as received on the CRC side. I wonder, is there really just no implementation that I can just like steal from Rust? Rust CRC Ethernet frame. Or I guess in the CRC docs, they had all of these like algorithm types. CRC 32. So what's like the name of the Ethernet CRC algorithm name? Okay. The polynomial is blah, 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 blah. Formal description is done from Ethernet standard 8023. Does any of these have like 8023 in here? Nope. Ugh. This has to be like one of the most asked things for this, right? CRC Rust. Maybe there's like an example in their like GitHub page. Custom algorithm, well-known algorithm. Well-known algorithm. It's like, surely the Ethernet one is one of these, right? Like it absolutely has to be. Like, but none of these guys are reading a bell. So let's like look at what these are. CRC 32X for CRC 32 Ethernet. Maybe this guy. It is starting to seem like just copy pasting this is easier than running this crate. But let's take a look and see at what these like custom algorithm fields provide us. Width is going to be 32. Poly, we have probably these are just false. What about like the X or out? Yeah, screw it. Screw it. We're just copy pasting the code directly and we're not using this library. So we'll say over here somewhere, we'll just say like function eth CRC. And we'll like just paste this guy. And I guess we should like attribute where we stole this from. Stolen and adapted from here. And we'll take in the data, which is a U8 slice. And start throwing these guys in here. So this is a mutable CRC. He has a polynomial. We say for b in data, CRC or equals b shifted left by 24. For this in 0 to 8 is the C++ way of doing this. Or not C++, what am I talking about? Rust. This needs some squiggly brackets instead of that. But shockingly, everything else is just the same. This actually translates really easily. And this should now return a U32. You can convert a U8 to a U32. So somewhere in here, he doesn't like this. There should be a U32. U32. And this should be this as U32 shifted left by 24. Now everybody should be working in U32 space, I think. And everyone should be happy. So let's see now if I calculate the CRC for my payload minus the CRC bit at the end, if we get the right thing. So let's just maybe here try to calculate it. So we'll say let calculated CRC equals eth CRC packet -4. Can I punch in a -4 like that? No, packet.len -4. Here we go. So let's print the calculated CRC here is this, and we'll print it in hex. And we'll go back to logging this again. So we'll print line frame or packet. I guess I should say. Frame's fine. Frame is fine. Okay. So let's see if we get the same thing. There's some problems here. So RTL 8139, he doesn't like this semicolon. 3860 doesn't like that, or main 360, because I have to call await on this get mac, which is stupid. This isn't an asynchronous function. So, oh, it is because it needs to lock. So we await. He doesn't like that though, because this guy is a non-synchronous function. So, or is a synchronous function. So we'll use the synchronous version of this for a second and just hope to God we don't crash. Build again. We spelled unwrap wrong. Okay, so we're back, we're running. And we calculated the CRC of, I printed it in hex, but this is not printed in hex. So let's go back here and look at where the CRC is printed. And we'll just print this in hex as well. And do these match at all? These are not the same. Fuck! Maybe the CRC is only on the payload? Let's double check that. Ethernet frame is done using this. CRC is plus blah, 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 blah. Standard sys receiver should calculate a new FCS data received compared blah, blah, blah. An alternative is to calculate a CRC on both received data and the FCS, which will result in a fixed non-zero verify value. The result is non-zero because the CRC is post-complement during CRC generation, since the data is received the least significant burst, and to avoid having buffer, blah, 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 blah. According to the standard, FCS value is computed as a function of the protected MAC frame fields, source and destination address, length, type field, length/type field, MAC client data, and padding. That is all fields except for the FCS. So the fact that I calculated this on everything and it's wrong means that I should take a second look at this guy. So there's some chances that there's like some overflow happening in here. And CRC as U32. Let's just see if that, let's just spitball if that's right. Nope, we're still getting the same shit. This guy in chat saying, one thing I noticed was that it noted that the least sig bit is sent first. Is that how you parse it from the ether frame? That's a good point. I did see that as well. I think so because my Ethernet least significant bit. The standard states that data is transmitted using least significant bit first, while FCS is most significant bit first. I mean, so yes, that should be fine because if this was backwards, oh, least significant bit, not least significant byte. Okay, an alternative is calculate a CRC using the right shifting, which result in C is here that is a bit reversal of the FCS. So let's try that. Good catch. Good catch. So we can do it with right shifting instead of left shifting. I thought, so when I read that initially, I thought that it was talking about bytes, not bits, and so I thought that I would like still see something similar. But obviously right shifting all the time is just going to result in 0. So I need to change my polynomial here to this guy before right shifting. If I print in binary, I guess we could spot. Yeah, that's a good idea. Let's try that first, I guess. CRC. So let's see, where is this guy? Ethernet frame, CRC. What doesn't T like here? So I can do hex, but I can't do Boolean. Rust print Boolean. Oops. Print binary. What am I saying? Boolean. Brains off. B formatting. So this should work. Colon B. Why doesn't it like that? I guess it's probably because of the debug formatter just won't let me. That's frustrating. I'll go back to trying the other thing first, where I swap my polynomial to the other one and right shift. So where was I seeing that? So I can say initial is, we can use this guy and right shift and see if that changes anything. So cargo run, we send a packet, we wait a second because I haven't taken that out yet, and my calculated CRC is Still not relevant at all. Lame. Lame, lame, lame. Okay, so we'll just go back and this has been done using a left shifting CRC32 polynomial 4xc. Where is my calculation function here? 4c11db7, 4c11db7, initial CRC post complemented, which I guess is this. Post complemented verify value equals 0x38fb. Where does this guy come from? The standard states the data is transmitted least significant bit first, while the FCS is transmitted most significant bit first. Okay. The standard states that the receiver should calculate a new FCS as data is received, then compare the received FCS with the FCS the receiver has calculated. Okay. However, hardware implementation of a logically right-shifting CRC may use left-shifting linear feedback shift register as the basis for calculating CRC, blah, blah, blah. Nasty. Okay. We will try printing these in binary. Hey, yo, what's up? So let's print this with a B here. We'll just confirm that this works. Let's take out that sleep. I'm tired of this. So in RTL 8139, we have the sleep in here, and let's just get this guy out of there because he is unnecessary now. So now I'm getting my calculated CRC in binary, and now we just want like the one we received in binary. What's a little tricky here is we don't know if they're sending big endian or little endian. I think that network orders big endian, so it should be fine to just take the whole thing and print it backwards, or print it forwards, I should say. But let's just take a look. I guess what we can do is, if we're not sure, we can say for byte in self CRC, we can say we write the CRC thing here, and here we can just say write F and print it as a binary. We take the byte that we just got and then drop a little off at the end. Which part don't we like? This. Cargo run. Okay. So the CRC they sent is 3 ones at the beginning, 3 ones at the end. We don't really see anything that resembles this at all in our calculated CRC, which is a bad sign. How are you doing? Writing a UDP stack? Well, we were trying to, but we got distracted by the fact that qemu, when it talks to us, is trying to use ARP to negotiate with us. And we haven't implemented like anything like that, so we're just kind of like figuring out like what the hell is qemu saying to us and trying to like send back a proper ARP response. And so now we've got stuck at the Ethernet CRC that's being calculated. We need to like put a CRC in our Ethernet frame when we send it back, and that means that we need to calculate the CRC, and we don't really know how to do that yet, so we're trying to figure it out. Ethernet CRC algorithm. I could have sworn that like that seemed reasonable what we got here. Let's see if like other examples. For byte in data. Oh. Okay, so they're just using the zlib version. Let's try using... Is there... Oh, no. Is there one of these that says, like, zlib? No. Oh. I presume that's CRC32, which is cursed because GNU had their own version at some point. I thought that CRC was just, like, normal. Like, I thought there was just like one CRC. I always thought up till now, but looking at this like CRC crate in Rust, there's like a million of them, which makes sense. There's like different starting points and stuff. I just was hoping that it would be easier than this. Clib CRC algorithm. I give up on that path. We should be able to just let's stop cheating. We'll just try to understand this correctly. So we'll go back to CRC and here we can see if we can find. Oh, here we go. Standards in use. Ethernet. This is just CRC 32, which is ISO 3309. Here we go. So we had CRC 32. Whoa. One of these, like 400 words in here, has to match this, right? bzip2. Let's try using the library that we had. So we'll say CRC, CRC new, CRC algorithm, I think it is. Or maybe just this. And then I think that we can say, oh, let's keep this here as in case we want to go back. And multiple items in scope. So we'll just say this, cargo check. This should be a CRC 32. Do I need to specify like U32 here? Yes. And then I can CRC calculate. What's it called? Hello? This guy returns a calculate data or something. It's not called calculate. It's called checksum. So what am I supposed to do here? I'm supposed to call new, get the digest, and digest.update, digest finalize. Oh, here, I can just call checksum probably. Checksum. We'll just return this as a 128, I guess. Oh, this is the 32. Cool. Let's see if this guy looks sane to me at all. Ooh, that's interesting. But there's a constant there, I believe, and that's what the versions are for. Yeah, that makes sense. Constant defined as pubconst, HLDC, blah, 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 blah. And if you had not mistaken that for the same constant you had before. Yeah, let's look. Let's look. So I was looking at the bzip2 one, but you were looking at ISO HLDC. What is HLDC in here? It doesn't come up. But let's look at what this guy says. So are there a difference between HLDC and bzip are different, and I think, where did my... Here's where the list was. These guys are saying that they all use the same. Ooh. All use the same field. So according to this, the bzip one and the Ethernet one are the same. From memory, try CRC 32C. Is this like, can I call this from Rust? Yeah, maybe. I think, well, first I want to go back for a second and I want to see, I think what I saw was that these are the same as what I had before. So I just want to see if, like, if I'm calculating the same as what the library is calculating now, we can be pretty sure that, like, the algorithm is correct and I'm checksumming the wrong data, or the checksum is wrong. So let's see. This is like calculated. This is the library one. Cargo run. Right, so like the fact that I'm calculating the same thing, I'm pretty sure these are the same. Let's make sure that these are the same length. So we'll just say calc. Oh no, these are different. Shit. I thought those were the same for a second. Okay. So let's try what you said. You said CRC 32C. And let's see if that gives me what I want. I don't like this just like blindly poking in the dark. I wish I had a better understanding. So this is CRC 32C data. And cargo run. See if we get anything useful here. Oh shit, CRC 32C requires standard library, which I don't have. Is there a feature to go no STD? No, there... Oh, maybe. Does look like they're using standard library directly in there. Oi, oi, oi. Oi, boy. So... let's take a look at these. Are any of these... I was trying to use this bzip2 version. And let's double check the Ethernet one here. He says he has a verify value of 38F. Do I find this anywhere in here? If I look up like this guy in here. Oh gosh, I lost him. No. 38FB. Yeah, I don't see that anywhere. I also don't understand what like the verify value on the CRC thing is yet. Post complemented, verify value, blah blah blah. Well, off to Rosetta code for CRC 30C. SIMD version or table lookup versions are faster, but the algorithm is 2 or 3 liner. Yeah, it really seems like it shouldn't be. It seems like it shouldn't be that hard. I don't know why I'm struggling with this so much. Usually, I don't have this much trouble with something this straightforward. CRC check. So yeah, why is this CRC algorithm? Like, I thought that it was just a few lines. Understanding CRC. Let's start implementation with just as close as possible to shift register approach. Yep. Nothing too crazy. I guess, let me read more carefully. So, we have a polynomial, initial CRC, post-complemented verify value. So I don't understand what this is. What's CRC verify value? Blah, blah, blah. Send the CRC value or the remainder to the receiver with the input data. The receiver has 2 options. It can compute the CRC via binary, or it can directly append the CRC value to the data. The receiver then calculates CRC using the entire input. If the remainder is 0, blah, blah, blah. So what is this like verifying value? That doesn't help me. CRC is post complemented. Verify value equals blank. Verify value equals that. Okay. Yep, so they're generated polynomial, blah, blah, blah. When a code word is received as read, the device here compares it, check the value, or if one for us to calculate the data block, blah, blah, blah. Blah, blah, blah. Verify. Values redundancy. Yeah, I'm missing something important here. Okay. Well, one thing the Wikipedia page is HLDC is the one that using internet. Oh, okay. Maybe I misread something. If you're claiming that you saw that matches, let's give it a shot. Because obviously what I'm doing is not working. So this is crc.checksum data. Oops, we should remove the CRC32 crate, so cargo run. So you're saying you pointed out this constant back here, ISO HLDC. And you said you search Ethernet in here. Oh yeah, you're right. I did miss that HLDC. But then why do I have bzip in here as well and see them being the same? But you are right that those were different in the library, and there's good reason to believe that you're right there. So let's take a quick little peek-skis. Where was I? I was in here. HLDC, ISO HLDC. Let's try it. CRC32 HDLC. Oops, not HLDC. Okay. So one zero one one, and we got 11101. Triple ones at the beginning, triple ones at the end. Not sure if the columns are defined correctly in lib, though. Not sure if it matches. Okay, let's just cargo run. So we calculated this triple ones at the beginning, triple ones at the end. We don't see that here. So once again, we're unlucky. I guess what we could do is we could just, if we want to get crazy, we could just try all the CRC32 variants here and see if any of them match. Right? We're getting a little crazy here, but we can say we can do this. So this is CRC, U32, new, this guy, print line, we print the binary representation of CRC checksum data. And if we just do these for all of them, let's see if any of them match what we wanted to see. So QQ, find this, we do this, and we just play out all of these guys in like this, and I just want to see if any of them are right. Assuming the lib is right, then we are likely doing the wrong data. That's my guess as well, for sure. He doesn't like some. Oh god, what have I done? Oh no. Something in here is unhappy. Let's start here. Cargo run. Okay, that worked fine. Let's unlock a couple more. So none of those guys are the one. Cargo run again. Yeah, so far none of these are matching what we get in the packet. But we have a few more to try. Once again, none of these matching. Cargo run. Test. Oops. Which one of these is causing this like bug to pop up? So yeah, I don't see any of these matching up. And it could be that I'm going crazy. Oddly, I think it doesn't like this extra version. Look at this for least significant bit, most significant bit first. Taking a look. However, the least significant bit is transmitted first, while the FCS is transmitted most significant bit first. Yeah, I get that, but we should be seeing if we're looking at the binary representation, we should see like one of them go backwards from the other, right? Unless they're not talking about least significant bit 0, like they're not saying how do I say this? Like, are they talking little endian, big endian, or like full on bit order difference? I initially was thinking little endian, big endian, but then when they started saying like least significant bit first, like no one does that, right? Like that's not little endian or big endian, so they must be actually just like full on swapping it. Ethernet transmit data with the most significant byte within it. However, the least significant bit is transmitted first. Oh. Ethernet transmits data with the most significant octet. Oh, this is fucked. Okay. Oh, but it's coming out. Least significant bit transmitted first. Sure. But at the I'm getting like the bytes. Each byte is in the right order for my processor as interpreted by the card, I think. Maybe this is like on the wire, but like as the card gets the data on the wire, it's getting the... It's probably just storing them big endian. Yeah. They do talk about swapping. Yeah, understood. Let's go back to hex printing. I think it's actually 0 to X is what I want. And here we should say like O2X, I think. And cargo run. Oops, we're not up yet. Testing. Building. What's happening? Oh, I just had it blocked. So calculated CRC, we're getting like this. And I do want to go back to like hex printing on the debug print as well. So we'll do like this. Just to check. Oh, here we go. We got, okay. So this is the CRC we got. This is the CRC we calculated. And I got a little confused here. Okay, so they're saying from Wikipedia, we have like, if we have in memory on our machine, my little endian machine, right? my little endian machine is going to have like we'll do hex at first. So these are like 4 bytes to make up a U32, and I have like 11, 12, 13, 14 or something, right? This is this number. Okay, well, we'll start with like an actual number. We'll start with the CRC that they've given us. I calculated this CRC, which is 1726 AC 72. So on my machine, if that's just like any U32, this is in memory as 72 AC, right? 2617, right? And they're saying that network order is big endian. So this is little endian. And so this is big endian here, right? If this is like increasing network order or increasing byte order. But they're also saying that within an octet, the bit order is reversed. So if I have like the number 0x1, that's going to be 000000001, and on the wire it's going to be 10000000. And where we got confused was I was thinking that if this is my number in RAM, like my number, it would first go big endian, right? And then I have to like reverse this whole thing. But the reversing is done by the card, the network card itself. So I don't actually have to worry about the bit order on the wire because the network card handles that. And so all I have to worry about is the byte order, which is big endian. And so we got confused trying to like flip between looking at bits and bytes and swapping and stuff. And it turns out that all we have to do is look at byte order. Easy. And so now we also have some proof that this like ISO HDLC is the one that will give us the right answer, because we're seeing the right answer now. And now let's also just quickly, just for my own sanity, I want to know if this like bzip version will give us the same answer. CRC 32 bzip 2. Because that page said that both the bzip version and the HLC versions, so no, that's wrong. Is that for every card, or should the driver fix that for some cards and some not? Yeah, I'm assuming for now. I can't comment on all cards for sure. I'm just inferring based on what I'm seeing with this very specific network card, the RTL8139, what I'm seeing. So, not sure, but it seems likely that for the I would be shocked if any network card that you plug into a computer would like not reverse the bit order for you, because that's like so inefficient to do in software but quite efficient to do in hardware. So it makes sense for them to do it for us, and it makes sense for them not to handle like big endian, little endian, because they don't know like how the data is going to be chunked necessarily. So I think that makes sense. I think that you could assume probably for most network cards that it would be byte order is correct, or within a byte order. I absolutely would not be shocked. Yeah, that's a good point. Okay, so that's sweet. We got to the point now where we tried a lot, right? And the end result was we're using this library to calculate the CRC. We've got our CRC down pat now. We are calculating the same thing that we got. We've kind of like proven to ourselves that we can parse an Ethernet frame somewhat. We know that like we're getting an ARP packet from qemu, and the ARP request is asking us to tell it. Sorry, brain melting. The ARP request is asking us to tell it our MAC address. Presumably, we're assuming at this point so that it can then give us the appropriate UDP packet. So hopefully, if we then send back the like appropriate ARP response, we will hopefully get back the UDP packet that we expect from qemu after that. So I'm pretty happy with that. My brain's like, I don't know if you guys could tell, but it's clearly not functioning very well if it's taking me that long to figure out how to like fucking CRC a packet. So I'm going to call it there. Thanks for watching. If you're enjoying what you see, you can always tune back in most days at around 2 Pacific time. I probably won't be streaming tomorrow, but I will be the day after. And If you missed the stream, you can catch me on YouTube. YouTube is linked in the Twitch description. If you're catching me on YouTube and you want to watch me live, you can catch me on Twitch, and the Twitch is in the YouTube description. So thanks for watching, guys, and catch you on the next one. Bye!